Thank you, Brian. Well, my case study, as Brian said, is fire and crowd evacuation modeling in a low-ceiling sport arena. It will involve FDS, Pathfinder, and hopefully a little bit of common engineering sense. At least I'll try. Now, as an introduction, this is my problem. In a few weeks from now, Iceland will host the European Team Gym Championships in Reykjavik. So that's an international event. It's a competition of 4 days. 1,000 participants from 20 countries. And the organizers, they want to have about 4,200 spectators. So you have to bear in mind that Iceland is a very small country. It's about 300,000 inhabitants. So we don't have huge fancy stadiums like there are in the States or in Europe. Most of the stadiums are used for handball or basketball. They have a capacity of 2,000 spectators maybe. Or we have some big indoor football stadiums, but without any sitting stands. So the problem is, in this case, there are no stadiums that are really suitable for this event. So here in the picture, we have what we call the Leadership Sport Arena. And this is an older hall that was built, I think, in the 1970s. It's used for handball and basketball mainly. And then a few years ago, they built this extension. And now, all that is called the Athletics and Exhibition Hall that is used primarily for training, exhibition, and concert. But it doesn't have any temporary stands, sitting stands. So even though it can, for concerts, for example, there can be several thousand people, it's completely different when those people are sitting in stands. So now we can say that the configuration is very different from its original. So we need a complete new fire risk assessment. This is when the fire authorities and organizers came to me and asked me to do it. Actually, this project is a bit special for me because that was the first project in this new company. I was just coming into it. And my company did it free of charge in order to sponsor the event. So I could do what I wanted with this project. I was using it as a training project also, to train, to see what FDS6 was and improve myself with FDS6. And also, when I came, they bought me this very nice 16 processors cluster computer. So I wanted to see how far I could go to the simulations. So for me, it was very nice to have this big project and try to protect myself with it. So the fire safety problem. So this is the hall that we will use. As you can see here, it is in its athletics for training configuration. So it's about 5,000 square meters. The ceiling height is curved, and it is between 8 and 11 meters, about 25 to 30 feet, if I'm correct. So walls here are made of concrete, and you have a steel structure for the roof. And we have 7 mechanical vents for smoke extraction. Evacuation doors, we have 18 different doors, quite good in order to accommodate some concerts. So we have plenty of doors available. So the organizer came to me. First, he contacted an architect and also a company called Total Event Solutions, a British company that was involved in London Olympics, who are actually renting these sitting stands. So this is the first layout, how they wanted it to be. They wanted to have 4,200 spectators. So you can see here are the halls, and here are the sitting stands, competition floor. Here's the main entrance area. And here you can see these 2 narrow passes that are used for athletes. They come in here and out here. So, and what I first did, I took my British standard, and I just counted the seats and the rows and to check if everything was, there was a British standard. And I contacted a specialist from this company, Total Event Solution, and about evacuation. He said, yes, I took the NFPA equations, a simple model, and it gave me 4.2 minutes. I mean, I like it when it's simple. Simple is good, but for simple cases. And in this case, I think it's too complex to just say my NFPA equations, that is basically an Excel sheet, is good enough. So for me, I wanted to look more into it. Especially, one thing that is quite important for me is it's a low ceiling area, so a low ceiling building. So for example, you see this little guy here, at the top is sitting on this stand over there, on the highest floors. And he actually has his head about 2.5 meters below the ceiling. So it means that you will see the smoke very quickly going down. And also, it's very densely crowded. The paths are a bit difficult. And yes, so everything, in my opinion, is it's a very good case where you can have panic. So NFP equations, they don't consider this. So now, okay, I had what my basic model, and now I wanted to know at what time people must have evacuated, so my critical time. So I used FGS. So this is my model, actually. So the domain is 100 times 75 times 15 meters. The door opens after 2 minutes with an intake of 28 square meters. We have 7 blowers. You can see actually here on the roof. They extract about 50 cubic meters per second. The mesh resolution, as I said, I was using this project a bit of self-teaching, and so I used 1 meter, 50 centimeters, and 25 centimeters mesh resolution. First, I wanted to check the mesh sensitivity, and then I also wanted to see how far I could go in parallel using the MPI run command. So maximum is about 7.2 million cells. And okay, these two ones, 1 meter and 50 centimeters resolution, it's calculated in Seoul. So design fire, always difficult, but I took a 10 megawatt medium, let's say a competition mattress. The fire is actually here in the center. So you have the fire, competition floor, and the sitting stands. So my criteria is visibility should be over 2 meters. Visibility at 2 meters. Well, we usually say above floors, but here it's above the highest row. So I think it's 7.5 meters in this case. I want the guy sitting exactly here. This is actually what is interesting to me. So and also, in order to test the robustness of my model, it's always simulated in normal conditions when everything goes well, and also in adverse conditions, in this case, when the blowers are not functioning. So here, mesh sensitivity. Here in this table, you have, okay, this stands for normal, so everything runs well. FDS 5 or FDS 6, and the resolution. And here, I actually plotted the layer 8 for every cases at the same position. So I wanted to see the evolution. The dotted line is FDS 5, and a plain line is FDS 6. So mesh sensitivity, what it tells me that my layer 8 stabilizes between 1.1 and 1.5 higher with a finer mesh. So remember, the little guy standing at the top as is at 2.5 meters below the ceiling. So 1.5 meters difference is huge. So definitely in this model, okay, mesh sensitivity is very important. Now, okay, I've been asked quite often, is FDS 6 better and how better? Well, I'm guessing Kevin and all these guys have been working very hard and implemented new models, so I'm guessing it's better. But I cannot say personally how much better. So I wanted to look a little bit more into it. And okay, what I found out here, if you compare, for example, these two blue ones, these two, is that the layer 8 stabilizes between 0.4 and 0.8 meters lower with FDS6 than with FDS5. Also, this is my critical time for every cages. And here you can see that this is FDS6, so the layer 8 forms sooner than in FDS5, so it reacts more to the mesh sensitivity. So, and also, a critical time is about 60 seconds shorter with FDS6. So I can't say at this time that FDS6 is better, but I can say it's that FDS6 is more conservative. And conservative is, of course, very important. What I tested also is CPU consumption, and FDS6 is requires much more CPU. It actually doubles the cost. But in my case, I mean, I gained so much precision with FDS6 and the finer mesh that it was worth this CPU cost. So I decided, okay, definitely, I mean, I knew I would take FDS6 from the beginning, but okay, I saw that the mesh resolution had a huge importance in this case. So I decided, okay, I will go down to 25, 30 meters and also test this new computer. So I've calculated now, this is parallel computation. So here on the left, this is the point of view of the little guy standing at the top of the AS row. So he will have his face very quickly. It will be facing the smoke very quickly. And also, this is the visibility at 2 meters above the highest row. So I want people evacuate before they meet this. Here you can see this yellow part. This is where my visibility is below 10 meters. So people must have evacuated before this happens above the stands. So I could say that this is after 670 seconds, so I can judge that this is my critical time. Also, I made the same calculation in adverse conditions with the blowers not functioning, and then I obtained 520 seconds. So these 520 seconds, I will use them as a reference for critical time and to see if my evacuation time is lower, hopefully, than this one. So, evacuation. I use Pathfinder. Remember, this is the original configuration that the architect designed with a company providing the settings. So I try, and this is my Pathfinder model. So this is the exact same geometry as with FDS, and I try to make it as close as possible as this one, especially regarding the age, other dimensions. So I have about almost 4,000 people in this case, and in each of the ISO, that is this one and this one, this is the most critical part. I have 70 people on these rows. So now, okay, I made several runs, and this is one of them. So this is actually my simulation after 3 minutes, and this is after 6. As you can see, we have a lot of congestion points around. These are the stairways. So we have congestion point at every stairways. But okay, it's like it grows when it goes higher in the row. So people here have to wait before these ones have gone into the stairways and evacuated before they can go themselves down. So this, you can see that even after 6 minutes, okay, this is almost clear, but you still have a few people still waiting to get into the stairway and evacuate. This is, okay, we can see it here on this graph. My pre-movement time is 2 minutes. So here you have the 70 people here and the 70 people there that are plotted. So okay, 2 first minutes, nothing happens. And then you can see that maybe 20 to 40 people can evacuate very quickly in the first time. But then it's like people are stuck for about 300 seconds. And then once maybe all these are clear, then they evacuate very quickly. So evacuation was completed after 440 seconds. So remember my critical time was 520. So I can say that the layout is fine if everything goes as intended. In this case, people are just waiting quietly for their turn, and it's a very polite and evacuation, if you could say. And as we learned today, this can happen, but let's not count on it. So what I did, this is my final configuration and the measure changes. What I wanted to do, I wanted people to be able to go out this way. They cannot cross completion 4 because there are some advertising panels, but I wanted them to be able to go down and this way. So I've created 3 passes that are 1.4 meters wide at these 3 ends directly in front of evacuation doors. So, and then, okay, I had a 1.5 meter wide passage. So a combination of these two gives me an alternative routes, so people can evacuate it easier, especially in case of panic. If someone falls, for example, in the stairway, people can still run this way. Also, one modification, we just move the stand a bit this way, because this is the main entrance, and as we know by experience, most of the people will try to go back the same way they came in. So we wanted to have more space here. So these are the main modifications. So now to my conclusion. Okay, if I look at just numerically, if we could say in this table, we can say that even in normal or adverse conditions, I still have sufficient time, about 78 seconds of safety margins. So I could say this is fine in a computational way. But still, I wanted to create some alternative routes to account for panic. You didn't say stupid, it was the other word, to account for madness. Stupid also sometimes. And okay, so finally, so we agreed with the fire authority that agreed to have this design with 4,200 occupants in the hall. And I could say that comparing FDS6 to FDS5, I cannot say it's better, but I can say it's more conservative. Thank you for your attention.
Thank you. Questions? Donna?
Thank you for a very nice presentation. I'm Donna from Israel, from SNetNL Engineers. We've been doing also some simulations for sport arenas, and I had some questions for you. The first one is regarding the combustion materials.
What I did, I have to say that I didn't look too much into it. I said I was putting a 10 megawatt medium fire that is, in my opinion, very conservative. And I don't exactly remember what I put as a combustion data, but I changed them as being quite a sooty fire. So also to be quite conservative and to be sure.
Okay, that was the first thing. The second thing, you've been using just 50 centimeters and 100 centimeters grid size?
No, I went down to 35 centimeters. Yes.
And you did a correlation between them with the variables?
No, I did with 150 to see the mesh sensitivity.
Okay, now the third question I have for you, well, it's a little long.
Sorry.
One was regarding the flame spread, because you've chose a mattress as a basic ignition fire origin. And basically, there is 2 things about that. First is what would ignite that mattress in the first place, and the second thing, if it's a gymnastic sport, as you illustrated in the first picture, it's a big mattress, which means usually it will spread furthermore than just in the middle. So this is something to take into account.
Yes, well, I know that competition mattress are usually they are made of non-combustible or I think hard to ignite material. As I said, I was not looking that much into with the combustion part. I was more interested in the gas phase in this case.
Okay. Last thing.
Yeah.
We've been writing notes here. Last thing is regarding your pre-movement time for egress.
Yes.
Did you calculate the time it will take? Because I didn't see you adding a pre-movement time for people to make their decision to start evacuating.
Well, I thought I mentioned it in this graph. Maybe I wasn't clear. Okay, I said it's about 2 minutes. I know, but nobody can say exactly, so I'm referring to what is said, code and standards. And
okay, thank you. I missed that. Very good. Very nice presentation.
Just a question on your graph. Can you help me understand why you have the sharp drop in the number of occupants egressing, and then a period of time goes by where it looks like nobody's getting out, and then another?
Yeah, I think, okay, that's a bit strange also to me. But I think at the beginning, some of these people here, it's just people that manage to go down just a few steps, that are not at these highest rows anymore. So I think at during the first seconds, a few of them manage at each stairs to go down. But then it gets stuck because other people in the lower 8th row, are already in the stairway. So the people completely at the top, they have to wait somehow that it gets cleared from the stairway in order. And this is so we have some bottlenecks, and we have some bottlenecks at every row. So first this bottleneck clears, and this one, and this one, and this one. And sorry. And at the end, then it's free to evacuate. I know that in reality, people will jump to the next row, and but this is why the model doesn't consider this. In reality, yes, they will just jump or move or try to find alternative routes.
And if I understand this graph correctly, what you're looking at specifically is like a top row, and that's
Yes.
the room, and you're counting people leaving the row. So as soon as they get into the stair aisle, they're no longer in the row. So
Yes, because somehow they are lower, so
Okay. Any other questions? And this will be the last.
sorry.
Hi, I have a question, and it might be more for Kevin and NIST as well. So we actually, quite often when we do the ASET, we look at visibility. And you say that FDS6 is more conservative for what you saw. And obviously with changes in the models, there's going to be changes in how things are outputted. Without using the soot deposition, some of my colleagues, not myself, have done some comparisons when they're in the middle of a design for FDS5 and FDS6. They've actually found that visibility has been more beneficial from the designing standpoint, meaning less conservative for FDS6. Not saying less conservative, but it's changed, and it's now actually showing that visibility lasts longer in FDS6. And I'm not sure if that's a trend that has been seen with FDS6, or if it's just parts in the model and it just depends on model to model how everything's been running.
I think this is a very interesting question. In my case, at least, FDS6 was more conservative. And I cannot, of course, probably Kevin can answer this better than me. And I think this is the kind of answer I want to get from this conference. Please.
I'll make it's hard to say case by case whether it's more conservative, less conservative. I think you can say that when you're dealing with situations like this where you have a relatively coarse grid, because inevitably you're doing this huge stadium, so you've got your grid is yay big on the fire. In FDS6, we're using what we consider to be a better turbulence model. So we get what I think is a more realistic plume, which entrains more air and dilutes more, which may explain why his layer came down a little further, because I think we're getting the entrainment into the plume better. If you look at old calculations with FDS4 and FDS5, if you had a really poor grid, I mean really crude grid, you would see the smoke go straight up instead of, meandering like a real smoke plume would. So with FDS6, I think we're doing better with the smoke plume dynamics. So that's going to dilute the plume more, which is going to tend to lower the temperatures a little bit more. It's going to increase the layer depth because you're entraining more volume. That may be consistent with what you're seeing, but again, it's going to depend case by case. But if I had to guess why you're seeing the results you're seeing, that would be my guess.
Yes, I should have maybe checked the temperature a little bit more to see if my layer 8 was slightly colder than
Yeah.
the 6.
Right.
I will definitely
And so if
take
your
it
if your soot yield is the same and your fire size is the same, then you're pushing is the same amount of smoke mass, but if your layer is deeper, that smoke mass is going to be, spread out over a greater volume, which may explain why the visibility is going to be better.
Okay, thank you very much.
Thank you.